nobody else has this week, so it's fine with me if we don't. I think you all had enough material from last week. All right. In that case, we'll begin on hypothesis testing, which is actually really apropos given a lot of the things we discussed today. In hypothesis testing, you have an opinion, you have a statement, a position, and you want to test to see whether or not that position holds water. And it can be about pretty much any of the things we've discussed today. The J curve has that particular shape. We can talk about the effect of currency on exports. We can talk about any smoking on lifetime or health, etc. Regardless, you have to phrase things in hypotheses, and then you have to gather data that sheds light on the hypothesis. So we're going to talk about a number of different types of hypotheses in the rest of this course. But for now, we're going to focus on two parameters of interest: the population mean and the population proportion. There are also two hypotheses we're going to have for every single test we're going to do: a null hypothesis, which is the baseline, that which is accepted if there is no other evidence, and, well, actually, that which is at the very least not rejected if there's no other evidence, and the alternative hypothesis, which you decide is true if there is sufficient evidence from your data. That leads us to two different types of errors we can make, creatively named type 1 and type 2, and we're going to go over that in excruciating detail. And then we're going to see how all those little arithmetic problems from confidence intervals filter through into hypothesis testing. You'll be happy to know, I think, that this material has nothing new mathematically. We've covered all the different arithmetic, all the different pieces already in confidence intervals, but in hypothesis testing, everything is backwards. So the interpretation is tricky. In fact, I would argue that it is the hardest material in the entire course conceptually. So it's kind of nice that at least math-wise it's not that tricky. And then finally, the last piece of the puzzle is the p-value, and that's probably as far as we're going to get today. Then we're going to deal with proportions and finish up next lecture. So it's literally a two-lecture topic, or two-class lecture. All right. So again, hypothesis testing, what you want to conclude with regards to a statement. So you start with a bias, prejudice, a position with regards to something. Now, it can't be something that you cannot test. If there's no empirical test possible, then you're not doing science, you're not doing statistics, you're not doing empirical research at all, or analysis of any sort. You're, well, doing something else. This is limited to that which can be tested with real data. Okay, the null hypothesis, which is almost always denoted with an H sub 0, is usually conservative. Not always, but usually. And most importantly, you have to have a test statistic and a distribution for a test statistic under the null hypothesis. What do I mean by that? You have to have a way to be surprised. You say you believe something is true, and then you get data. If the data is just really surprising compared to what the null hypothesis is saying, that leads you to question the null hypothesis. That's the logic. Court of law, the null hypothesis is what? Innocence, right? Innocence is actually the null hypothesis. You then get evidence. If the evidence is sufficiently at odds with the null hypothesis, you reject the null hypothesis of innocence, and you conclude that the individual is guilty. Right. Now, in a court of law, what is the only other verdict?
Innocent.
Nope.
On the jury.
Not guilty. There is never a verdict of innocence. There is a verdict of not proven in Scotland, but I've never quite figured out what that's for. In the U.S., you can be found not guilty because there's not evidence beyond a reasonable doubt, right? which means the jury has not said you're innocent. It could very well be that you're guilty, but just not enough proof. There's not enough evidence. Yes? Now, that might sound a little strange, but the fact is, the only thing that you can positively say in a hypothesis test is when you reject the null hypothesis and you positively state that the alternative hypothesis is true. So, how you frame your hypothesis determines what you can say, what your conclusions can be. If you had a null hypothesis of guilt, then you were supposed to, then, if you reject the null hypothesis, conclude that the person is innocent. The problem with that is you can't very well prove a negative, right? Logically, it's impossible to prove a negative. So you can't have such a structure for a criminal system. On the other hand, it's been tried before. It didn't work very well. And there are all sorts of ways that you can tweak the criminal justice system based on this framework. This framework, literally, and it doesn't matter which one came first, but the analogy is perfect. You can do pretty much anything in, or you can find an analogy for pretty much everything in hypothesis testing to a criminal trial. And that's usually helpful because most people have a much more intuitive feel for a trial than they do for statistics. Okay, so the alternative. The alternative must be such that between the two hypotheses, you have a collectively exhaustive set of possibilities. One or the other must be true. However, they're also mutually exclusive. So if one is true, the other is not. There's no overlap at all. Okay, that covers that. There are two types of structure here, and in most cases, when you talk about hypothesis testing, you are interested in research hypotheses. These are statements that you want to test because you want to show that they're false. Remember, the null hypothesis can be rejected, but you cannot conclude that the null hypothesis is true. All you can conclude is that there's insufficient evidence to reject the null. So a research hypothesis you would tend to put as conservative and, like for instance, if you're dealing with a marketing campaign, somebody tries to sell you, actually even better, snake oil. Somebody tries to sell you snake oil. This will cure everything known to man, and then some. What's your position when somebody suggests this might be true? But in words?
It's not true.
It's not true. Very good. Okay, so if somebody tries to sell you a marketing campaign saying this will increase your sales by 20%, you should, at least from a business perspective, have a similar position, right? They haven't proven anything yet. So your position then would be, no, the null hypothesis here is that your campaign won't do anything. It won't increase the sales at all. It might even decrease the sales. And then you let the data speak. Now, the data would therefore have to give you an impression that not only does it increase sales beyond where you are right now, but enough beyond where you are right now that it wasn't just a fluke. Right? We're going to control for the flukes here. That's the key part. In a research hypothesis, everything that we've just said makes, fits that structure. And that would be for a marketing campaign, if somebody claims that their medication works in a certain way, if somebody claims that, actually pharmaceutical claims are all put in hypothesis testing format. But there's another type of claim. What if you own a business and you have a supplier that has sent you parts every month for the last 5 years? And you've never had a problem. But just for due diligence purposes, you take out a small sample of doohickeys every month and you measure them to make sure that they're the proper weight, or let's say proper weight. And this time you found that, let's say it was a bottle and it was from Coke, and you found that the average weight of the bottle was a little less than what the mean was supposed to be. Does that lead you to conclude that the entire shipment is bad? Now, when I say a little less, I'm talking about so little less that it won't have any impact on you selling the bottle onward, and there's no legal problem. Because you're right.
It's insignificant.
Right, it's insignificant, and you've got an ongoing relationship, right? You're doing this again and again and again. You're just trying to see if there's sufficient evidence for you to conclude that there's a problem, rather than trying to see if there's sufficient evidence to conclude that there's any impact whatsoever, right? So with the manufacturing hypothesis, the next one, then these types of claims, you tend to give them more of the benefit of the doubt, and you see whether there's sufficient evidence to disbelieve their position. Now, the hardest part in hypothesis testing seems to be coming up with your null and alternative hypotheses. And it's sometimes very hard, but if you remember these two different structures and ask yourself, the first question you should ask yourself is this a research claim or is it a manufacturing claim? Is this a one-off deal? Is it an ongoing relationship? Okay. The other two things you have to remember, be conservative and make sure that you have some distribution of test statistics, something you can observe that will tell you whether or not you should be surprised. Like for instance, I could have the hypothesis that this class is going to last until June. And then I show up here in May 12th or whatever it is, and nobody's here. That would be surprising, right? If my null was true, it would lead me to question my sanity. At the very least, reject that null hypothesis. Okay. Obviously, we're going to have to look at various examples of this. Okay. And when you make a decision, whether or not you've done set up a research hypothesis structure or a manufacturing hypothesis structure, that's critical, right? In a research hypothesis, you typically won't do anything. You're not going to buy a marketing campaign unless you have rejected the null. With a manufacturing style claim, you'll typically just accept what's going on unless you actually reject the null. And then, of course, you have to do follow a completely different set of actions. These, I don't know why, this is done that, and I thought I'd saved it correctly, but apparently not. Of course. Okay, so these are the only hypotheses that you can have with means. Notice the equality part is always in the null hypothesis, and we'll talk about why that has to be very briefly. But this is it. There are no nodes. So these two are one-sided, and the last one is called a two-sided hypothesis, or hypothesis test. And also notice that if you have the null hypothesis listed, the alternative is given. Right? Because between them, they are collectively exhaustive and mutually exclusive. Okay. So here we have an example with an emergency system for a hospital group. They have 20 mobile medical units, and they have the ideal that they should respond in 12 minutes or less. Okay. So the director sets up a test that he's going to do every week or every month to test whether or not they're reaching their service goals. So first of all, is this a research claim or a manufacturing claim? Is it a once-off or ongoing?
Ongoing.
It's ongoing. And so it's
Manufacturing?
it's a manufacturing claim, right? Because it's something you test again and again. It's like quality control. You don't want to upset the apple cart unless you have good evidence that something's wrong. So, with that in mind, what is the null and what is the null hypothesis?
Whether the mean is greater than or equal to 30 minutes.
No, because that would mean that there is a problem, right? By default. Yeah. Yes, and it is very important to have the equality there. It's also crucial, and somehow, for some reason, about a third often make a mistake on this. Hypotheses are always about population parameters. They're never about X bar. This is completely uninteresting, because if you haven't gathered your sample, X bar is a random variable. It may or may not be less than 12 the next time you gather a sample, but It's certainly not less than 12 in general. If you've gathered your sample, X bar is just a number. You don't need a hypothesis to test that. You can just look at the number. So no matter what, hypotheses are always about population parameters. Mu and population parameters in particular. Now, if this is the null hypothesis, what is the alternative?
Mu is greater than 12.
Very good. Everybody see that in that case, collectively, the two hypotheses are collectively exhaustive and mutually exclusive, right? One of these has to be true, but only can be true. All right. So that leads us to our next question. Our type 1 and type 2 errors. And there's no way to sort of just give you an example that covers everything, so we have to go and first introduce a lot of terminology. Type 1 error, that is rejecting a true null. Type 2 error is failing to reject a false null. So, in this case, a type 1 error would be what? Well, no, if this is the null hypothesis, what would it mean to have committed a type 1 error?
Greater than 12.
Well, yeah, a little bit more. Okay, so we conclude that mu is greater than 12 when in fact mu is less than or equal to 12, right? Your conclusion is what makes it an error, yes? Okay, everybody see that? If you conclude that this is false when in fact it's true, then you've made an error. I think everybody can agree on that. But what you can't agree on, this is just a definition, is that that type of error is called type 1. And it's vastly different from type 2. So look at this. Type 2. Or you can look at this, it doesn't matter, both of these together. A type 2 error would be concluding that this is true when in fact it's false. So in this particular case, it would be that the emergency medical services were not providing the service you need, or within 12 minutes, but you concluded that they were. That would be a type 2 error in this context. And these two are not the same thing. Let's assume that we have a large sample size. Why would that be useful? Central limit theorem. So the sample mean time taken is normally distributed. We're going to test at a mean of 12. And we'll talk about why that is shortly. Now, if you find a mean, let's say you found that your ambulances took 10 minutes. Would that make you question this null hypothesis? No. That's consistent with the null hypothesis, right? If your ambulances took 18 hours to respond, you really don't need statistics to conclude that there's something really wrong here. Yes? Okay. The only point at which statistics does something useful is somewhere here, in the gray area. 12 minutes and 1 second. Could that be a fluke? Of course it could be a fluke. In 1 hour? No, it's not going to be a fluke. 45 minutes? Probably still not a fluke. At some point though, 15 minutes, 14 minutes, 13 minutes, 12 and a half minutes. At some point, you're going to have trouble saying, okay, this is a fluke, this is for sure, this is, you don't know where to put the cutoff. And that is where statistics is useful. Because this methodology will allow you to precisely control the uncertainty. And it will tell you exactly where to put the cutoff, so that you don't have to use weasel words. What you can say is, we are 95% confident that the services are spending longer than 12 minutes on average in the population. Or you can say we failed to reject the null hypothesis at a 5% level of significance, which we'll talk about very soon. The question is, how do we find that number, right? And that is where alpha comes in. That is the level of significance. And what we're going to put here, we're going to call the critical value in terms of x bar. So CD equals critical value. And the reason that I put the subscript there is that we're also going to come up with a critical value in terms of z, and that's the one we're going to focus on primarily. Now, the way we get that is as follows. We're going to also create a rejection region, which is an interval such that if our test statistic is in the rejection region, we reject the null. And we're going to create one that's in terms of x bar and one that is in terms of z. But that rejection region, in terms of x bar, is going to be from the critical value from x bar to positive infinity, and in general, it's going to be from the critical value to positive infinity. So, time for another question. Area under PDF, and this is under the validity of the null. So area under a probability density function represents what? Probability. So what does this area represent? What kind of probability?
0.
No?
The probability of exceeding the critical value,
Yep. What happens when you exceed the critical value?
you reject your null hypothesis.
You reject the null hypothesis. And it is the probability of rejecting the null hypothesis under the validity of the null hypothesis. So the null hypothesis is valid, and you reject the null hypothesis. What does that sound like? Just talked about it. Type 1 error. That is what we call alpha. It is the probability, actually the maximum probability of making a type 1 error. Okay. Is it possible that we'll make it a type 1 error? Yes, of course. We could get an average response time of 20 minutes. It could happen. No matter what, that could happen, or even 5 hours, when in fact the null hypothesis is true. But somehow we have to come up with that cutoff. And that cutoff is alpha, or is driven by alpha. One thing that is crucial to note is there's a vast difference between numbers along the real number line and areas. You choose alpha, that gives you the critical value. In this class, alpha is going to be chosen by, well, me. In reality, it's typically 5%, sometimes 10%, sometimes 1%, but if it's anything other than those three, that would be one of those, you've got some explaining to do cases. Okay? All right, 1 minus alpha, you'll recall, was the confidence level. Now, the question becomes, how do you represent the probability of making a type 2 error here? And that's tricky. The reason it's tricky is you don't really know which distribution to use, right? There are all sorts of distributions that are valid under this hypothesis. In fact, any mean greater than 12 is valid. But we need to pick one just to demonstrate. And let's pick this one. So this is one possible PDF under the alternative distribution. And what really ends up happening is that you calculate beta for every single distribution. Okay, now let's say the mean is here, so that we're not confusing the two things. All right, so the critical value is not the mean. What is this? What am I shading in now?
That is the probability that
Good start.
thanks. That your null hypothesis would be concluded as true when it's not?
That's right. Very good. Because you're no longer getting a test statistic in the rejection region, right? So you're failing to reject the null hypothesis under the validity of the alternative hypothesis. So this is the probability of making a type 2 error, which is called beta. Does everybody see that there is some sort of relationship between alpha and beta? Like if we move the critical value to the left, I'm sorry, to the right, alpha is getting smaller, right? What's happening to beta?
Larger.
It's getting bigger. And if we move the other way, the reverse happens, yes? Now, and you can see that since the heights are different, it's not a one-to-one relationship, right? But the real question here is there a way for you to make alpha and beta smaller at the same time? Both alpha and beta. Well, right, these are both probabilities of making errors, so we'd ideally like both to be 0, right? And that's not possible in the real world. But we can make them pretty small. We can make alpha arbitrarily small if we put the cutoff out here, right? Just like we can make the beta arbitrarily small by putting the cutoff down here. But even if we leave the critical value here, we can make alpha and beta smaller. How?
Number of samples.
Yes. That's always a great answer in statistics. Increase your sample size. What happens when you increase your sample size? Yes, excellent. The distributions become tighter, right? Around their means. So essentially what you're seeing is that instead of having overlap like this, all of a sudden you're getting something like this. And it's much easier to tell apart. So the reason is, again, the standard error is sigma or the square root of n. So if you increase n, you are decreasing the standard deviation of x bar, and then you find that it's much easier to tell apart. Well, it's much easier to avoid both type 1 and type 2 error. But that means that alpha, beta, and n form a triad. You can choose 2 of those, but not 3. If you've chosen 2, the other is given. So you basically have 2 degrees of freedom in those 3 parameters. Okay. Questions on that?
Can you say that, what's the probability of error?
Beta is a probability. It's a probability of making a type 2 error. So it's the probability of failing to reject the null hypothesis when the null hypothesis is true. I'm sorry, it's false.
Probability of
Failing to reject the null hypothesis when the null hypothesis is false. Which leads us to another question. What is 1 minus beta? We talked about 1 minus alpha, so stands to reason 1 minus beta is something. Start with the distribution. Is beta something that exists under the alternative or the null hypothesis? Alternative, right? So under the alternative distribution, so this area is 1 minus beta, right? So it's under the alternative hypothesis, it's the probability of getting a test statistic in the rejection region, and in other words, doing what? type 1 error would be under the validity of the null hypothesis. If the null hypothesis was true, and you rejected the null, that would be a type 1. Now the alternative is true, so the null hypothesis is false, and you reject the null hypothesis. Make sense? Okay. If the null hypothesis is false and you reject that null hypothesis, then you've not made an error, right? It's a good thing. It is, in fact, the ability of the test to identify a false null hypothesis. Think of this again in a court of law. It's the ability of the test to identify a false null hypothesis. What was the null hypothesis in the trial?
Guilty. Not guilty.
No?
Innocence.
Innocence. And then a false null hypothesis then would be, right. So it's the ability of the system to identify somebody who's guilty. And they call that the power of the test.
Can you say that one more time? It's the ability of the test to identify.
A false null hypothesis. Like I said, this particular area has a lot of different pieces to it, and the problem is too, it's all one big whole. You pretty much have to swallow it as one large chunk, because if you try to do it in pieces, the pieces of themselves don't stand alone. Not well, anyway. All right, questions? All right. So, I found this very useful when I first learned about this type of structure. Remember, there are only two things you can conclude, right? You can fail to reject, and it is very important that you write fail to reject the null rather than accept the null. You never accept the null. Or you reject the null hypothesis. The population condition, in other words, real life, the actual what's going on, is either that the null is true or that the null is false, right? Those are the only two possibilities, which means if you fail to reject the true null, you're good to go, as you are if you do reject a false null. But if you reject a null hypothesis when the null is true, you made a type 1 error, and the probability of that happening is beta. If you fail to reject a false null, then you made a type 2 error, the probability of that is beta. What did I say over here?
Beta.
Oh, alpha and beta. But that also leads us to another point. If you have rejected the null, is it possible to make a type 2 error? No, because you're in this row, right? The only possibilities you have are either make a type 1 error or that you were correct. If you fail to reject, similarly, you can't make a type 1 error. It's not possible. You can either make a type 2 error or you were right. Yes? Okay. And in a court of law, you can, in fact, make it virtually impossible to make a type 1 and type 2 error by adjusting the propensities to find someone guilty or not guilty. Right? Why do we, okay, when we have a jury, and instead of having a majority jury, which exists, I know it exists in France and certain other places, we insist on a unanimous jury. What's the effect of insisting on the unanimous jury in a criminal trial? Does it make it harder or easier to convict?
Harder.
Harder. So, what does that do to alpha?
Shrinks it.
Makes it smaller.
Makes it smaller, right? It makes it more difficult to incorrectly find someone guilty, right? Finding someone guilty who's innocent, that's a type 1 error, and that makes it's more difficult to do so if you insist on a unanimous jury verdict, right? However, what effect would that have on beta? Makes it larger, right? insisting on a unanimous jury verdict will lead to having more guilty men on the street, right? And in this particular case, I'm perfectly comfortable using the word men, since again, we pretty much dominate prisons. Or certainly all of violent crime. If you keep this matrix in your head, or at least on your crib sheets for the final, that'll help you, I think, quite a bit in making sure you're managing. Is there a way to make alpha 0 in a court of law?
Confession?
No, because you have lots of false confessions. It's easier than that.
Mistrial?
No. No, it's easier than all this. I'm talking about systemically. So you're designing the system of justice. Is there a way for you to force alpha to be 0?
Bench trial?
What's that?
Bench trial?
No, because judges make mistakes too. It's easier than that. You basically do away with the entire system in the sense that you have everybody be innocent, or you don't put anybody in jail for it. And you think, well, that's completely unrealistic. Well, one, it's been tried. It's called anarchy. Doesn't work terribly well. But it's also used in certain subsets of criminal trials, like for instance with the death penalty. Death penalty cases in a lot of, in fact, almost all OECD countries is simply, it just doesn't exist anymore. So you no longer, at this point, of course, you have an alpha 0. Can you make beta 0?
Yeah.
How? Convict everybody, that's right. And Stalin did a bang-up job of that in the 30s. Also not a terribly successful experiment. Although apparently his star is rising again in Russia.
Well, it worked for him.
What's that?
It worked for him.
It's true, it did work for him. Not so well for the 30 million that he did away with, but you know. So yes, you can sort of make alpha and beta pretty much whatever you want, but you get the system that you've designed. In most civilized countries, we end up with controlling alpha and making that quite low, and then we let beta be what beta is going to be. So if you get somebody who is guilty but is really close, there just isn't enough evidence, they're far more likely to get off scot-free than us putting away somebody who's innocent. At least that's the design. Okay, the last conceptual topic we're going to deal with is p-values, which we will get to after the break.